Welcome back, ladies and gentlemen. So, in this video, we're going to be checking out this idea of potential energy and how certain types of forces can change that potential energy. First of all, the idea of potential energy. It's a very broad broad category of energy. And there's a symbol, typically a capital U, is used to represent this. Recall that with kinetic energy, this symbol was a capital K. Now, sometimes you'll see this KE for kinetic energy. For potential energy, sometimes you'll see a PE for potential energy. And the symbol is not terribly important. Our textbook uses the capital U and the capital K for these two. But it is possible that you'll see the PE and the KE. Same idea. Now, the idea of potential energy. I think of this as a way of storing energy. And we can store energy in an object, for example, by placing an object at a greater height. If we have a tabletop here, we're going to put this object up on that tabletop. So we've raised it, and we're storing some energy in this object now by putting it up at this new height. There's another way we can store some energy. Think of food. And when you eat food, you've got these different chemical bonds, chemical reactions taking place. And if you might have like a six carbon ring here, for example, maybe a sugar molecule. If you are changing the chemical bonds, you might be storing energy. Your body uses glucose, glycogen for immediate energy. Long-term energy storage would be in fat molecules. Okay, so you get the idea. Chemical bonds can store some energy. Also, we could, for example, stretch a spring. So if you have a spring at a resting length and you stretch it, then you have stored some energy in that spring. The spring is going to be able to do something for you with that stored energy later on, possibly. By the way, the same works if you compress a spring. You would take a spring of a certain length and squeeze it. Same idea. You have stored energy in that spring. Cool. Well, what we need to consider, though, with this idea of potential energy is that not all forces are going to allow us to store energy like this. You'd think that if you are pushing a box across the floor, for example, you have your applied force, and you're going to move this box a certain distance here. Okay. Well, according to the work energy theorem, we're doing work on the box, and our work done really should be changing the kinetic energy of the box. If it starts at, say, some initial velocity here and ends up with some final velocity over here, you would think there's this delta V taking place. We've accelerated the box. We have changed the kinetic energy. Well, the real world doesn't let us do that sometimes. We understand that there is definitely going to be some friction acting against us, and so we'll see kinetic friction. And the issue is this: the kinetic friction we see, and sort of by the connection between these two, then we're not storing any energy in the box by moving it in this way. Friction is a non-conservative force. It doesn't really work to store energy for us. This force that we're applying really is only necessary to overcome this friction. And so this force we're applying cannot store any energy in this box by moving it in this way. So the work we're doing is simply work needed to overcome friction that develops when the box starts moving. It is possible, because there is a maximum value of the friction, it is possible to apply a larger force and therefore actually accelerate the box and so on. But even so, we really wouldn't be storing energy. We would be having kinetic energy built up in the box, but that's still not really a form of storing energy. What happens with the friction, also you can think of the friction as sort of stealing the energy from the system that we're dealing with. So something about this idea of storing energy here's another way to distinguish forces that are conservative versus non-conservative. Only conservative forces will store energy in this way, in some way. We are specifically going to be looking at two types, two examples of forces that will be able to store energy for us. So these two specific forces, and these are conservative forces. First one is gravity, and we in the previous video we looked at gravity, and we came to understand that when gravity is doing work on an object, say you're moving an object from one place to another, the pathway you take to get that object to the other location does not determine how much work gravity does. The work gravity does is independent of the pathway. That makes gravity a conservative force. There's another type of force that is conservative, and it's the force we see in springs. So we're going to look at these two examples, these two types of forces, very specifically. Now, there's this idea, though, that we have to come back to, and it is the work-energy theorem. We're going to take a second look at it, and basically, if you are going to use it, you're going to have a conservative force storing some energy, then the work done by that conservative force is going to equal the amount of energy stored. But here's the way this works out. You have an initial amount of stored energy, and you have a final amount of stored energy. And it's written this way. This is interesting. This is not a final minus initial situation. And so if we look at this and we want to sort of relate this to a delta U, a change in the stored energy. Well, if we were to factor out a -1, we basically get to flip these around. So factor out a -1 and you get final minus initial, which means you can talk about the change in stored energy, the change in potential energy here. So the work done by a conservative force, that's what the subscript C is indicating, conservative force. Work done is equal to the opposite of the change in energy. Now, keep in mind, work and also energy, they are not vectors. They don't have a direction. But both work and potential energy can have negative values. Maybe I should specify, work can have negative values. The change in potential energy can have negative values, but an actual amount of potential energy stored really can't be a negative value. You'll see this. Really, the focus is on the change. This is what really matters, the amount of change in potential energy. So work getting done is going to change the potential energy of the system. So let's look at some examples here. First example, we'll deal with gravity. So let's say there is this mountain. You want to get to this mountain peak, and you've got this climber. Awesome. And what the climber's doing is we're going to have, from the climber's current position to the peak, there's going to be a change in height of 100 meters. Nice round number for us. So the deal, though, is the elevation at the peak is, let's give it 4,301 meter above sea level. And this peak elevation comes from Pikes Peak, which is, I believe it's located in Colorado. So how about the elevation where the climber starts? Well, we just take off 100 meters. 4201 meters is this climber's starting elevation. So we're going to look for, as the climber ascends to the peak, what is the change in gravitational potential energy for our climber. So we're looking for this in the form of gravity. Okay. So essentially, if gravity is the force, we know it's a conservative force here, then the vertical distance from here to here is in the upward direction, and gravity is working in the downward direction. So what we should see is the work done by gravity is going to be a negative value, but what we should see is the stored energy of the climber. As the climber ascends and goes higher, the stored energy increases in value. It should be a positive delta U. So from the relationship here, where the work done by a conservative force equals the opposite of the change in potential energy, well, we're going to see that the work done by gravity is going to be a negative value, and so we're going to have a positive change in the potential energy of this climber. So how do we work this out? What's the relationship here? Well, it's actually quite simple. With gravity, the work done by gravity is simply going to be mass times gravity. So there's a force, and we have a distance. Now the distance is basically going to be a change in our vertical position. So we rewrite this, and this is typically how you see it: mass times gravity times the vertical distance traveled. That's why we call it a y. But this is going to produce for us this change in potential energy. All right. So let's work this out. We have a current level of potential energy at this elevation, and we have a new potential energy at this elevation. And so we can work that out for ourselves with say, a final and an initial vertical position for y values here. So we're going to say, well, this change in potential energy is going to be final value for minus initial value. And so, well, you know, what if, let's say the climber's carrying some stuff, they have a significantly, nice significant mass, 82 kilograms. G is 9.81. And our final position is the elevation at the peak of the mountain. Okay. And so again, for the initial values here, mass times G, and our initial elevation, 4201 meters. So when we work this out, we get a value of just over 80,000 joules. Okay, that's quite a bit of work done. Or I'm sorry, quite a bit of stored energy. That's what we're looking at. The change in energy from this elevation to this elevation. Interesting thing that we can do with this problem, though. We took our initial. I'm sorry. When we were doing this, we're kind of saying, well, where would the baseline value be? So somewhere far down below, you've got sea level at 0 meters elevation. Okay, so we have at this 0 meters elevation, the stored potential energy would be 0. And so we took at this beginning elevation, in this component of our equation, the climber had some stored energy already, and at the final elevation here, they had some new amount of stored energy, and we just found the difference between them. Awesome. And this is using sea level as sort of our baseline for zero. Well, another way to look at this is really pretty simple. What if instead we took this initial location to be our 0 point? Okay, well then what is the change? What do we do here different? It turns out, well, we just say we would start in an initial vertical position of 0 meters here. But then what is the new position? We would simply say, well, the new position is 100 meters above that. And so here we would change this to 100. And it turns out you're going to end up getting the exact same answer. So what this is showing us is it doesn't matter so much where your 0 point is, where you put your origin. All that's really going to matter for you is, do you get the correct change, that 100 meters? So we can look at that change being from 4201 to 4301, or we can look at that change being from 0 to 100. Same effect. Awesome. In the next example, we're going to look at the energy stored in a spring. Now, what we know about springs already is that the work done to compress a spring is equal to 1/2 kx squared. And where x is the amount of compression or stretch done to the spring. Well, springs, the force in a spring is a conservative force, and so we have work done by conservative force here. And that work done by conservative force is going to equal the opposite of a change in potential energy. So there's something that's often done. Where the spring is at equilibrium length. Okay, here's our beginning x. Equilibrium length. No compression, no stretch. Then that's usually where we will say our U final is 0. And the reason is this. If we stretch the spring, if we elongate it, then what we're concerned with is the force that the spring will generate. And the spring is going to want to pull back to this final position, so that this would be our initial position. And there would be some initial amount of stored energy in the spring. And so if we have final minus initial, then the work done by the spring is a certain value, and it's going to be equal to the opposite of that change in potential energy. Conversely, if we take the same spring and we have an initial resting position, and we're going to say, well, at that equilibrium position, the stored energy is 0. And if we compress the spring from that position, just to there. So what the spring itself is going to want, we've applied a force this way, but what the spring wants to do is rebound back. It wants to come back here. There's our force of the spring. I missed that in this diagram, sorry. Force of the spring. And so here at this position, there is an initial amount of potential energy in the spring, and as it goes back to its equilibrium position, we will see that we will see a decrease in the amount of energy stored. And once it reaches this location, this equilibrium length again, there's no more stored energy. Okay. So, what's going on here? We can work this out with an example. I'm going to need some more space here. So we're going to say with a force of 120 newtons applied to a spring, we're going to create a stretch of 2.25 centimeters. If we kind of just draw this out. Okay. So we create this stretch. Let's say we're going to pull on it. And from an equilibrium length to a new length, we have applied this force. Now this is our applied force, and we have this stretch of 2.25 centimeters. And our applied force is 120 newtons. And we have to maintain that force in order to maintain this stretch of the spring. So we want to look at the potential energy of the spring when it is compressed by 3.5 centimeters. So we're going to try to find the potential energy of the spring when compressed by 3.5 centimeters, or the potential energy of the spring when stretched by 7 centimeters. Okay. Well, something if you look at what we're doing here with our final value of stored energy being 0 at equilibrium length, in all these situations, final value at equilibrium length, the stored energy is 0. What that does for us is in this equation, I'm gonna just take this over here now. We have this relationship where the work done is equal to the opposite of final minus initial potential energies. And we know that this guy is 0. Okay, so the work done is simply going to be equal to the work done by the spring, I should specify. Work done by the spring is going to be equal to the opposite of negative initial energy. So the equation simplifies quite a bit here. The idea is this: we need to first figure out our spring constant. So do we have enough information to do that with our current situation? We know that a force applied by a spring I almost went the wrong direction with that guy, is going to be negative kx. So we have the force that we're using, and if we're holding it here, the spring is in equilibrium, so the spring is going to be applying a force trying to return. Ew, this thing is terrible. There's no force of the spring. Okay, I'm going to have to stop using that marker. But that's okay. We also know the amount of stretch when we are using this force, and so we can figure out the spring constant. We have this relationship here, and the spring constant is going to be we have 120 newtons divided by 2.25 centimeters. Now this will give us an answer in newtons per centimeter. We would really prefer this to be in newtons per meter. So this is going to be 0.0225 meters. All right. We have a spring constant of 5,330 in round numbers, newtons per meter. There's a value for K. Awesome. We're going to need that. Because what we're going to do next is try to identify, to answer this first question right here, how much stored energy is there when we have compressed the spring by this distance? So we go back to the relationship here, stored energy in the spring, and usually the I is dropped, and we just write a U. So stored energy in the spring is equal to 1/2 kx squared. Pretty straightforward with this. So stored energy, 1/2 kx squared. Now, when we're answering this question, though, the x is not the 2.5 centimeters initially. This was just used to allow us to find the spring constant. Now what we have is a compression here of 3.5 centimeters. And yes, if you're really concerned with things, you might say, okay, well, to the right is going to be a positive direction. But look what's going to happen. Yes, the compression would be in the opposite direction. So you might think, oh, I got to change the sign. I'm going to get a different sign on my answer. Well, you're not, because x is going to be squared, and any negative values are going to disappear. And now we know the spring constant, 5,330 newtons per meter. And in this case, x is the 3.5 centimeters. I will want that in meters. Please don't forget that exponent. It's so easy to lose track of an exponent like this once you're plugging numbers into an equation. So we end up storing 3.26 joules of energy in the spring when we compress it by 0.35 centimeters. Now, what about stretching it by 7 centimeters? Well, we'll take a look. I mean, you might just look at the difference here and have a guess as to the answer. We're going to have a displacement of the spring that is twice as much. And we compare these two, right? So here, this next x is equal to twice the initial x that we had, or twice that. So is that going to double the stored energy? No. If you're paying attention to what's going on in the equations, you'll see it already. So in this case, the stored energy, we'll come back to the same equation, kx squared. K is the same, 5,330 newtons per meter for that spring constant. Now our x value is 7 centimeters. Convert that to meters. So what is this? Oh, don't forget the exponent. Please don't make that mistake. And okay. With this much stretch now, we see that there are just over 13 joules of energy stored. And if we compare that to the previous problem, the previous situation where we wanted to look at a compression of 3.5 centimeters. Okay, so did we see a doubling? No, we didn't. And the reason is, when we check this out, the difference, what we saw, K was the same. But what we did was we doubled x here. And the exponent had to apply to both. And that's why we saw 4 times the amount of stored energy instead of twice the amount of stored energy. 3.26 times 4 would get you through 13.1, round numbers. So we see that gravity, the work done by gravity, can either, well, okay, the way I should say this, work done by gravity is actually not going to store energy in something. The work done by gravity is going to release stored energy. It will reduce the gravitational potential energy of an object. And that comes back from this relationship where the work done is equal to the opposite of the change in energy. So the work done by gravity itself is going to decrease the stored energy. The work we do against gravity will increase the stored energy. It's kind of the same with springs. What we see with springs is that the work that we do with our force will increase the stored energy of the spring, and the work done by the spring itself will decrease the stored energy of that spring. So you have to be very specific in how you phrase these relationships. The work done by the spring or the work done by gravity are going to be decreasing the stored energy. The work done on the spring or the work done against gravity will be increasing the amount of stored energy in our system. That covers work and potential energy. Thanks for watching.